High-frequency trading is a big industry. To give you some perspective, the New York Times estimates that high-frequency trades account for 51% of all trades made. And it's imperative that these algorithms are tested. For example, Knight Capital in 2012 lost $440 million in under 45 minutes because they deployed an algorithm that hadn't been tested. Historically, only trading companies have had access to the infrastructure to allow them to test their algorithms. We propose a system that will allow people to easily develop and test their algorithms on their home PC.
To illustrate how our engine works, I'm going to run through a quick example. This is a sample algorithm using a technique called Bollinger Bands. That doesn't really matter for this example. The programmer interfaces with the market using our market view class, which provides a full interface for listing stocks, obtaining stock prices, and selling stocks. We've also created a selection of value objects, which simplify algorithm implementation by performing common tasks on behalf of the programmer. Here the programmer has chained a couple of value objects together to calculate the moving average and the moving standard deviation of the mid-market price. These are evaluated on demand at every tick of the simulation. When the algorithm tries to buy or sell a stock, the test engine posts a bid or an offer to the market as if the algorithm were interfacing with the real market. At the same time that the trade is posted, the test engine captures a snapshot of the trade so that we can later analyze the behavior and performance of the algorithm. After the algorithm itself is written, we can prepare a configuration file for the test, which chooses the types of performance indicators that we're interested in, how we'd like them displayed, and also adjust simulation parameters. You can imagine an algorithm that's highly tuned to a carefully selected parameter, and you could find that value simply by varying the configuration file and then running the test a number of times. Finally, we can run the test client, which connects to our test server, where the tests are run against historical data. The results are returned as requested, and we get immediate feedback. We can see that this particular algorithm needs a little fine-tuning. It hasn't quite managed to make a profit. The optional JSON output can also be used for further processing, or it could tie into a continuous integration platform for algorithms in the industry.
One of the problems we face during development is that the data we're using is purely historical. Here's an example.
Oh, you pressed up. You pressed it. Okay.
Pretend there were 100 of some stock. Historically, the market might make an order to buy 75 of them, leaving only 25 remaining. What happens if we bought 50? When the market came in to buy the 75, how many should remain? The answer is that we keep a track of everything we do. We have some ghost orders. So we buy a 50, we apologize now, that top 50 should be a 100. We do not change the number of stocks in the market. Instead, we remember a negative 50, and when we present the market to the user, we simply add them together. When the market then comes in to buy it 75, we cancel off this ghost order, and the market remains consistent and never deviates from the historical. The consequences of this is that the market is oblivious to all the user's actions. This means we have to make the assumption that the user's algorithm would have very little impact on the market if it were ever run.
Another problem we had is that we had expected full market data feed from the exchange, but in fact, about 5 weeks into development, we found out that we were only being provided with historical aggregates, which didn't have the sufficient information to match the trades, as Lawrence suggested. Luckily, we'd written enough of a modular design that we were able to only change the database schema and I think re-implement one interface without actually needing to change the interface of the algorithm at all. So that actually wasn't a problem for us, but it could have been bad. Since the beginning of the project, we've been using Git and GitHub for version control, hosted on a private repository. Using Maven, we managed to automate the building process of our project so that the build could be performed without any developer assistance. We also set up Jenkins, which is a continuous integration system. On every single commit of the new code, Jenkins would fetch changes to our project from GitHub, rebuild our project, run unit tests, and automatically email us if anything failed. This made changes to the server very quick and painless for us. Finally, if we were to proceed with this project, we'd love to increase a greater range of performance indicators. We'd love to add more value objects to make development even easier, and perhaps offer a nicer user interface for the user so that it could be integrated well within a game environment.
Thank you very much.
That's all.